Good morning, I'm Marco Cognetti and this is the pitch video of Chair Control Active Perception for Human-Assisted Navigation by myself, Marco Agravi, Claudio Pacchierotti, Paolo Salaris and Paolo Rubufo Giordano. In this work we propose to combine the ability of a mobile robot in autonomously maximizing the information acquired by the onboard sensor for improving its estimation with the high-level skills of a human operator. This is achieved through an active perception algorithm that is fused with the operator skills through a shared control approach. In particular, the active perception algorithm generates a trajectory that in our case is a cyclic B-spline that maximizes the amount of information coming from the robot sensors. In the meantime, the human operator is in charge of modifying, online and in real time, such geometric properties of the cyclic B-spline. Also, the operator will receive a feedback pointing in a direction where information is maximized, or, that is the same, the estimation uncertainty is minimized. Our approach is composed by 5 tasks. The information task, that is the Gramian task for maximizing the information coming from the robot sensors. The B-spline length that constrains the B-spline to have a constant length necessary for having a well-posed problem. The flatness regularity, since we assume that the system is differentially flat for avoiding the numerical integration of the model of the robot. The state coherency for ensuring that the trajectory always passes over the current robot position so as to not generate tracking errors, and the user task. We stack them in a prioritized stack of task approach where it's possible to note that the user has always a higher priority with respect to the Gramian. This is for ensuring that the operator has full control over the genetic properties of the path, and therefore the feedback generated by the active sensing represents a suggestion on how the robot should move for improving the estimation performance. The output of our controller deforms the trajectory and computes new input for the robot. The latter will move according to the provided input, and it will acquire the new information about the environment. Diff is an observer, an extended Kalman filter in our case, that computes new value for the state and the covariance matrix that, together with the human operator input, are the inputs for the novel iteration of our controller. As it can be seen by the scheme, the controller provides the human operator with a feedback that, as mentioned before, provide a guidance towards which the estimation performance are improved. We test our approach in different scenarios. The one shown in this video is a power grid activation, where the operator should activate 4 electrical switches. We compare 2 working conditions, N, where the constructivity Gramian maximization task is not considered and no feedback is provided to the user, and CGV, where the constructivity Gramian maximization task is activated and the visual feedback that will be denoted with a green arrow is provided to the user. In each video, the VREF view is shown on top left. The estimation error of the extended Kalman filter is displayed on top right. A view of the operator that interacts with our framework through an haptic interface is shown on bottom left, and the minimum eigenvalue of the inverse of the covariance matrix of the extended Kalman filter that provides a measurement of the maximum estimation uncertainty is displayed on bottom right. The point that the operator controls is depicted in green. A switch is considered activated when the real robot passes on the center of the switch. However, the user does not know the exact robot position, since the operator sees only the estimated robot. The switch to be activated is depicted in red. Once it is activated by the real robot, that again is not seen by the user, it becomes green, and the next switch to be activated becomes red. In the end condition, the user has difficulties in activating the switches due to the estimation errors, and she has to do different trials for fulfilling the task. In the CGV condition, the user is able to fulfill the task in an easier way in less time with respect to the end condition, thanks to a reduced estimation error. The results confirm the validity of our approach. In this paper, we propose a shared control active perception algorithm aimed at combining the high-level skills of a human operator with an autonomous controller whose goal is to minimize the estimation uncertainty. The operator is in charge of modifying online and real-time some geometric property of the curve. Moreover, visual haptic feedback is provided to the operator, guiding him or her toward the direction where the estimation uncertainty is minimized. We evaluated our framework in different scenarios, performing a comparison with a framework that does not consider the active perception task and or does not provide any feedback to the user. This comparison confirms the effectiveness of our methodology and the usefulness of providing haptic or visual feedback. Thank you for your attention. We will be more than happy to reply to your questions.